hello, in today's lesson we are going to be introduced to set theory. Under here we have the terminologies that we are going to use. Before we look at the terminologies, we know that a set is a collection of objects which are related. Terminologies which we are going to encounter as we deal with this topic here. The first term which we shall encounter, we have members or elements of the set. So that's the first terminology, and I'm going to define it, but based on an example. If I have set A, which is a set 1, 2, if I have set A which is equal to 1, 3, 2, 4, 6, then 1, 1, 3, 2, 4, 6 are the elements. The short way of saying this is like using this symbol. The symbol here shows that 1 is an element. This symbol can be used to mean element. So here someone can say 1 is an element of set A. So that 1 is here. Someone can say 3 is an element of set A, and so on. The second terminology that we are going to encounter, subset. Set A is a subset of set B if all elements of set A are set B. Take an example. If set A equal to 1, 3, 5 and B is equal to 1, 2, 3, 4, 5, 6, 7, we say that set A is a subset. This is the denotation of a subset. Set A is a subset of B. Reason being, all elements of set A are also found in set B. Empty sets. They don't say empty sets. There is an advanced word they can use as a noun. This is a set with no element. It is always denoted by those curly brackets and without anything inside. Or the next terminology that we may encounter is a finite set. Finite set is a set whose elements can be counted. For example, D, which is a set of days of the week. We have 7 days of the week. They can be counted, and such a set, a finite set. Another example, F being the factors of 12. Someone can list the factors of 12 and exhaust them. The opposite of finite set is the infinite set. This is a set with uncountable elements. Example, W representing whole numbers. We cannot exhaust all the whole numbers. Another example is a set of real numbers. There is no bound, and so many others. The next terminology, number of elements in a set. Now, if we are to talk about number of elements, that means we are going to consider a finite set. So number of elements in a finite set can be just counted, or elements in a finite set can be counted to get the number of elements in that particular set. E.g., I'm going to give a finite set here, set A which is equal to 1, 2, 3, 4. The number of elements in set A denoted like A into bracket capital A is equal to, we are just going to count the elements which are inside here. So these are 4 elements. The first element, second, third, fourth. So we have 4. Another set can be B, which is equal to. So we have a set B here. Number of elements in set B is equal to. We're just going to count the elements which are here. So when you count, there are actually 7 elements in here. The next terminology, union of sets, denoted by beta here. The union of 2 sets is the set of all elements that are members of either set. Example 1, given that capital M is equal to, and capital N is a set which has elements 3, 4, 6, 7. We are required to list M union, the number of elements in the union. of M. Now to get a set M union N, we are going to write the elements of these two sets. So the first step before we write the union is to identify the elements which are belonging to the two sets. We have 3 and 4 belong to set M and N. So those ones have to be written once. M union N therefore becomes 1, 2, 3, 4. 3, 4 is also in these other sets, so we can't write it twice. Jump to these other elements. So a set M union N, part B, part A is done. We are required to find the number of elements in the union. Number of elements in the union, we are going to count this, and we count 1, 2, 3, 4, 5, 6. So we have the union of the two sets. The next terminology, intersection of sets, denoted by that this is a set of shared elements. We also have an example, given two sets, A which is equal to -1, 0, 4, 6, 5, 7, and B which is a set -1, 6. Find number of elements in A union B. At B, find A intersection B, and hence number of elements in A intersection B. So here, before we find the union A union B, we have to identify the shared element. -1 appears there and there, seeing a 6 appearing in the two sets. So -1 and 6 are the shared element. What does it mean? It means A union B is now a set. -1, 0, 4, 6, 5, 7. Then we pick these other elements from set B. It should be having sets from elements from either set. Number of elements in A union B now becomes, the count is 1, 2, 3, 4, 5, 6, 7, 8. 8 elements. That they say find A intersection B. A intersection B, those are our shared elements, and we have seen we have -1. Number of elements in A intersection B. Next terminology is disjoint sets. Two sets are said to be disjoint if the intersection is an empty set, e.g. P, which is a set 1, 3, 5, 7, and Q, which is a set 2, 4, 6, 7. So we say that two sets are said to be disjoint if the intersection is empty. The intersection is an empty set, e.g. P is equal to 1, 3, 5, 7, and Q is a set which has elements 2, 4, 6, 8. So we need to prove whether these two sets are disjoint. So to prove this, we have got to show that the intersection is an empty set. So we can better do this by representing the two sets on the Venn diagram. So I have set P here, I have set Q. Set P has elements 1, 3, 5, 7. Set Q has elements 2, 4, 6, 8. So because there is no element in the intersection, this simply means that the two sets are disjoint. You can see that the number of elements in P intersection Q equal to 0. This implies that P intersection Q is an empty set. Hence, P and Q are disjoint set. The next terminology, we have complement of a set. So if we have two sets which are in such a way that maybe set A has some elements which do not exist in set B, then those elements which do not exist in set B are a complement of set B. Here I have an example, illustrate what I'm just saying. Set A has elements which are A, E, O, U. Set B has elements A, B, C, D, E, F. So members which are present in B but not present in A are said to be complement members for set A, denoted as A with a prime or A with a bar on top. So basing on the two sets, we have A is here, A is there, E is here, A is there. A complement is what we are looking for. We don't have C here. C is in set B. That means C is a complement. C is a complement of A. It is in B, but not in A. Here I have B. B is not in A, so therefore B is a complement of A. B here I have capital B and A. So all these elements are the complements of set A. They are not in set A. And in A complement, the number of elements in A complement is count the elements which are there. They are 4. We have the universal set. This is a set which contains all the elements of an item under consideration. Venn diagram, we have seen something about the Venn diagram. So the Venn diagram is used to represent the regions of two or more sets. Represent the regions. So we are going to start with a two-set problem. After we have exhausted the two-set problem, we shall shift to a three-set problem. So we have two sets, A and B. The universal set is always going to be on top there. Universal. If this is set A, we shall have it being represented there. Set B, we have set A, set B. Then in the middle here, this is A intersection B. We talked about complement, saying that if set A is here, set B is here. Members which are in B but not in A are complements of set A. So members who are here but not here are complements of set. Let's go back there and then we see what we are going to complement. In this region, you can see that there is no member, there is no any member of set A. Because the whole of this, you can see this over here is for set. So if we happen to shade it off, we shall not have any member of set A. So that means this region here is to have a complement intersection. The same reasoning comes to this, the whole of this over here for set B. So if you happen to shade it, meaning that you will have removed all elements for set B and it will be remaining with only elements of set. So this will be written as set A intersection B complement. Then the region outside here, if you are interested in the region outside here, it means you are going to shade this, the whole of. It means you are going to shade the union of A and B. You shade this if you are interested in the region out. So what does it mean? It means that the region outside here is the complement of the union of A and B. So we have A union B complement. Or we need the region outside here. It means we don't want A complement intersect. It also means we don't want B complement. So these two things are equivalent. This sometimes this is B only, as you are going to encounter those. This here is A only. You cannot find any member of B in this region. This here is the intersection, and outside here is the complement of the union. Alright, this has been introduction to sets, majorly two-set problem. First of all, we have to understand more about a two-set problem before we advance to the three-set problem. So in the next video, we are going to have many examples about a two-set problem, and then we shall advance to the three-set problem. Don't forget to subscribe and hit the notification bell for more inspirational and academic videos like this one in mathematics. Please see you next time. Thank you very much.